Okay, so it seems that most of you have connected. I have started recording, so we can move on with the next topic. This is basically the second lecture on the cluster analysis. And we will cover some more methods, more topics regarding the clustering itself. I have quite a bunch of pages to cover today, so I guess that we will stay a bit longer than usual, but I guess this became usual already. Yeah, but just need to cover a few methods in order to explain completely the diversity and options that you can choose for the clustering algorithms. So, okay, let's start. I will put my whiteboard on. Okay, so hopefully you can see it again. I hope you can hear me well.
Yes, all good.
Yep, great. So hopefully we will not have any issues today, because this is not what actually happens all the time. Okay, so today we will go into the some more methods for the clustering. Specifically, we will talk about the classical soft clustering method, which is called EM algorithm. We already have seen EM as a separate steps for the k-means clustering, but there is a slightly different approach in the EM algorithm, because it mostly is used for the Gaussian mixtures. So EM algorithm for Gaussian mixtures. Basically, in scikit-learn, you can look up and see the Gaussian mixtures. This is the algorithm that you can use in order to unmix a few Gaussians. I will give you a hint how to actually find out how many Gaussians are there, so you can try to use various methods or metrics in order to determine the number of clusters. Just like we did before, but these methods that I will show you around are more involved. They actually try to reduce the complexity of the algorithm. As well, this is basically the other name of the EM algorithm you might find apart from Gaussian mixtures. This is so-called Gaussian mixture models, GMM. This is, okay, modeling, Gaussian mixture modeling, and so on. Actually, I have to make one note that there exists soft clustering. So this is basically a soft clustering where we will be look at the probability of the cluster K, probability to be in cluster K, given the observation Xi. Right, so we want to have this probability. So for each cluster, 1 to k capital, we'd like to know what's the probability of this particular observation to be in a certain cluster. So basically, we want to have these probabilities expressed in from 0 to 1, just not like we had in hard clustering having just 0 or 1. So basically, this was a hard one. I have to make a note that there exists a possibility to use the soft clustering for k-means. So k-means modification, k-means mod for soft clustering. It's called fuzzy k-means, or soft k-means. This is not a huge, it's a slight modification of a k-means algorithm. So I basically want to skip that in order to save our time and to get into the more complicated case. This is where we have a model. We have an assumption that our observations are a mixture on a certain model. So basically, we do an assumption that data are coming from K distributions of the normals. So basically, we're looking at the in 1D example. So for the first example, for the first observation of the and description of an algorithm, we will be talking about the 1D example. 1D example for the simplicity, right? And this is basically dimension equals 1. Right, because it's easier to draw, it's easier to explain, and once you will know how it's actually handled and what's the algorithm, what's the essence of it, then we will turn into a multivariate case. So this will be something like an addition to that. So basically, we have one Gaussian. So you can imagine like the powder or the sand is actually pouring from this direction, right? Falling sand, or let's call it a white sand, right? Which is very common in Lithuanian beaches. So it's pouring from here, right, in the center. So you can assume that this Gaussian has a center. So this will be a center x1, let's call, right? And this pile of the white sand will be, we will call it k equals 1. This is the first cluster, right? So basically you have some sand, you're pouring on a table, and you have a very nice, normally distributed pile of the sand. Okay, so close to that pile of the sand, simultaneously, you would be pouring another pile of the sand, right? And this, let's say, can be from the famous, for instance, black sand beach somewhere in the Black Sea, right? So basically, you have a different kind of sand, and you're pouring. And this is the center where you're holding your hand or whatever cup you have for the sand, right? And this is x2. This is the location that you're pouring at. So it's normally distributed, floats around, and this is your cluster number 2. And here you have only the black sand, right? On this side, here you have only the white sand, and here you have a mixture of both, right? So points that are here, somewhere here in between, they are mixed between the two piles. And now imagine that you don't have actually a color of the sand, right? So no color, only just the location of the points, right? So basically the sand is here, somewhere here located, right? And located over here, right? So basically more sand is obviously at the center, right? Distributed. And towards the tails, just like the normal distribution, right? You have just less and less particles, because particles are not falling too far away from the center, right? So basically you have these piles of sand somewhere like here. So this is the highest density of the sand particles, and these are going rarer and rarer towards the ends. Okay, so basically this is how it is actually expressed with two piles. And once you don't have the color of the sand grains anymore, and you want to distinguish which is coming from where, right, you have to do some kind of a clustering to actually determine that this pile is coming from one distribution, from one beach, right? And this pile is coming from another distribution, from another beach. And they're just mixed together. Okay, so this is basically x, right? This is our first dimension, which is in d equals 1, which is the only one for the simple examples. And here is the probabilities, right? The probabilities expressed in the normal way. Okay, so as we already have talked about the normal distribution is actually expressed in 2 parameters mostly. So the first parameter is a center. This is the average of the distribution, and the other one is basically the variance, right? So variance is basically difference from the center. So this will use sigma squared 1. Sigma squared 2. So basically, if we want to express these two. Okay, so basically, if you would like to calculate the probability, you have to use something like the normal distribution density function, which is expressed as the capital N, and you have to provide the center, right? Center and sigma, obviously, right? Sigma for the K, right? For the K, and this is so-called probability. Okay. Probability density function. Okay, this is a probability density function, and this actually expresses the probability of our observation, if observation to be at the cluster K, which is equal to probability of the if's observation to be at the cluster, which is expressed by the center of the cluster and variance, right? So given center and given variance, what is the probability for this observation to be in this cluster? Okay, so basically we can express that, we can continue that, and I will write once the function, which is quite big one. You don't need to memorize this, but anyway, for 1D I have to write it down. This is 2p sigma k squared and E by degree of xi. This is the observation minus x minus difference from the average squared divided by 2 sigmas k. Okay, so this is something like a function which you can calculate for the specific point, and you will know what's the actually probability, what's the height of this function at a given point. Okay, so basically to write it down, we will be using a few so-called posterior probabilities. Posterior, which is a probability under a given condition. So there is a condition for the probability calculation. So basically the one we just throw down, right? This is the probability like this. And this is a probability of observation xi, right, given k. Okay, the other way around, we can say that this probability to be in the K's cluster, then given the observation. So this one is probability being in to be in K cluster given xi. If you have this observation here, so what's the probability of this observation being in that particular cluster, right? So basically this is a way around, and these two probabilities are called posterior probabilities because there is a condition. These are condition probabilities. That's why they are called posterior probabilities. Okay, so we will be using another probability. This is a prior. So the probability for the cluster, it's actually called weight of cluster K, weight of cluster K. In EM, in mixing algorithms, it's called a mixing coefficient. And this is actually an overall probability of observing a point in K. overall probability observing points or samples, right? Samples in K. So this is basically the importance of K in the mixture. And how we can express that in this graph. So this is basically the height of the graph, right? This is the height of the graph. So this graph has a height pk equals 2, right? So this is the height of this distribution, and this is the height or importance of how many observations are there, right? This is a prior. This is the pk equals 1, right? Okay, these are the heights of this guy. Okay, and these are so-called prior probabilities. Okay, and there is a rule that since we have a mixture, so prior probabilities, the importance of clusters actually sum up to 1. So basically, there is a rule that if we take k equals 1 until k, so k is number of clusters, right? So this is number of clusters, right? Number of clusters. So basically, these all priors are equal to 1. If we sum up all the heights, right? So these need to be balanced, right? These need to be balanced. So if we don't know any information about the point location, so we just say that our point, the majority cluster is basically the highest one because it's the most important. It has the largest weight in our mixture of the normals. Okay, so given these things, right, given these probabilities, and since we already know how to calculate the one posterior probability of observation xi given k, right, and it's equal to the probability to the normal, right? So normal, let's put it normal probability density function. And by the way, this can be any model, any distribution model. If you would make an assumption, if you would assume that your samples within the cluster are distributed given to the other distribution, so you can basically change it here, right? So basically you can change, so you would get a different graph, a different distribution, and so this EM algorithm would adapt to the different model. Okay, so this assumption, we already have made an assumption about the distribution, and we try to apply this into our model. Okay, so now we need to calculate between these guys somehow to convert. We need actually to do what we need to do. We need to calculate from this guy, from this posterior probability into this probability, right? Because what we actually are looking for, we need to know how much influence does for the given cluster this xi has. Okay, so in order to do that, we actually need to turn into the sideline here and to talk about the bias theorem or rule. Bias theorem or rule, because we want to do some calculations here. And basically, bias theorem or rule says that one posterior probability of A given B, right? These are two independent events. So probability of A given B, this is familiar that we had before, is calculated by the probability of B given A times of probability A, right? Times of probability A divided by the probability of B. Okay, so basically, again, we have probability of A and probability of B. It's called the initial probabilities or priors, or initial probabilities. And these guys, probability of A given B and probability of B given A, posterior. posterior, or A after B, and so on, right? The posterior probabilities. Okay, so basically derivation is actually made quite simple. There is a very simple derivation and we can prove it, and it comes from the definition of the conditional probability. And the conditional probability states that probability of A and B of observing two independent events is actually equal to the probability of observing an event A, which is independent, event A, times probability of observing event B given A, right? So if A is already present and we're observing B, so basically multiplying these two guys is giving us the probability of observing both events at the same time simultaneously, or one after the other. So it depends on actually the subject. And it is coming from the specification of the conditional probability. Let me write it down. Conditional probability rule. Rule is actually that PA given B, right? Observing A given B is equal both events, A and B, divided by BB. Okay, then of course BB must not be equal to 0. Okay, so basically after this we can derive that guy. From this conditional probability rule we can derive that guy, right? So we have this as number 1, right? This is number 1. So basically we can do the other part. With number 2 would be PA and B equals probability of B times PA given B, right? So this is vice versa, the same like 1, but vice versa. But actually these two probabilities are equal, right? So what we can do, we can basically put the probability of A, B given A, right? And it's equal of probability B, probability of B given A. No, I made a mistake here. So of A given B. Okay, so this is basically a simple rule that we just have these two parts equal. So basically we equalize these two on the right-hand side of the function. So now we just basically can have the probability of, just like we did before, probability of A given B equals the upper part probability of A, probability of B and A, right? So this is vice versa and divided by probability of B. Just basically we got the same thing like we wrote here as a bias rule. Okay, so basically this gives us a way to inverse these posterior probabilities, right? Because this here we have the probability of xi given k, and we want to calculate the probability of k given xi, given our observation. Okay, so good. Okay, the other rule which I want to show you briefly, this is a called rule marginalization, or law of total probability, law of total probability, right? Law of total probability. And this law actually states that probability of observing A equals to sum from 1 equals I equals 1 to okay, A, basically let's call it A, where we have all the possible options of observing both probability A and B, right, which is A. And basically we have A coming from 1, no, this is I. Let me put it like this. I coming from 1 to A, and these are the all possible options. options, right? All possible options for A. So basically, we observing something, and the event which we are looking for. So basically, if we have all the options, right? We have all the options exhausted. So basically, we can sum up these probabilities, right, of ANDs, and this will give us the probability of observing the event, right? So basically, for instance, to see some event outside, so to see a child, it is the child without a parent, with the child with the child walking alone, child with a mother, child with a father, and child with the one of the grandparents, right? So these are all the options that I can observe a child. So probability to see a child is basically the sum of all the probabilities seeing them together with parent or grandparent. Okay, so basically this is a law of total probabilities that basically we sum up these probabilities together. Okay, so I'm just giving these two rules, the bias rule, bias theorem, and this law of total probabilities for you, that basically we will be using them quite a bit. Okay, later on. Okay, so you can basically derive all the functions. Okay, let's make a small example now, and I would ask you to do some calculations right now regarding the bias rule. So basically, let's do a small example. So basically, F is a fire. Let's tell S is a fire, right? And S is a smoke, right? And B is a barbecue. Now it's the springtime, so people are quite eager to go to the barbecue place to have the hot dogs and wherever else. So basically, you can observe a smoke coming from the barbecue or from the fire, right? Okay, let's say that probability of observing a fire is quite rare, right? So let's say the probability of observing a fire is something like 1% probability of observing a fire, right? Probability of observing a barbecue, let's exhaust it, right? Let's take it 1 minus probability of fire, right? So this is 99%. Good weather, finally it's warm outside, so basically there's a very, very high probability of observing a barbecue. Okay, so now probability of having a smoke given a barbecue, let's say it's not that often, right? Because now we have these various liquids burning the coal, so it's quite rare that we see the fire coming up from the barbecue. So let's say it's 50%, right? Given the 10 barbecues, 5 would be with the smoke, 5 would be without smoke, right? But the probability of smoke given the fire is very, very high, right? So this is 99%, right? So basically, once you have a fire, the probability of smoke very, very high, right? Even though the fire itself is very rare. Okay, so let's now calculate the probability, posterior probability of fire given a smoke. Basically, if you have a smoke somewhere, if you observe a smoke, basically, what's the probability of the fire there, right? So let's calculate it. So basically, calculation is made so that we have, again, following the bias rule, probability of smoke then fire, and probability of fire, right? So we basically follow just blindly the bias rule. And here we need to calculate the probability of smoke, right? Probability of smoke. So in order to calculate the probability of smoke, we need to use the law of total probabilities. So we need to sum up probabilities of happening both events, right? So this actually a calculation probability of smoke given fire, probability of fire, right? So this is one probability, right? This is probability of seeing smoke in the fire itself, right? Both together. plus probability of smoke and barbecue and probability of barbecue. Right? Okay, now try to calculate it. Try to calculate this and write down into the chat the answer. Yep. Good, Gabius. So the probability of fire, if you see a smoke, is actually just 2%. Even though that probability of the smoke when the fire is very, very high, but since the fire is so rare, so that we just have a 2% probability, right? 2% probability of it actually being a fire when you observe a smoke. So obviously, if we do the calculations for probability of barbecue giving us smoke, right? So we can repeat it. It would be again, okay, let me probability of smoke then barbecue, probability of the barbecue, and here just the same thing. Please calculate it quickly. Plus probability smoke and barbecue, probability of barbecue. Because we have calculated it once, so you can calculate it very quickly because this is denominator is just the same. So we just need this part to go up. And since we don't have any options for the smoke to be observed by any other, I think you think that the denominator is wrong. Okay. Smoke and fire, probability of fire plus probability of smoke and barbecue. You say that these numbers are wrong? I have put it wrong. But Gabius has calculated it correctly, so I don't know. This is 99, this is 99. The first part should be PSB. Okay. Yeah, so basically this is just a this is a sum, so it doesn't matter which part is coming from. Yeah, so obviously since we don't have any other options, observing a smoke for any other reason, right? So there are only two reasons here. We have a complete system because we just made a here the complete system. So basically observation of the probability of being a barbecue when we see a smoke actually is 98%, right? So 98%, so 1 minus previously defined. Okay, so I guess you have got an idea. This was just an example of calculating simple calculation for a bias theorem. So we basically, what we did, we have inversed the conditional probability. So now let's go back and try to calculate and try to write down the probability of being in a cave cluster given xi, giving the observation of I. Right, so basically, again, this is quite simple now because we know already the bias theorem, right? And we have made an exercise here. So basically, we have a probability of xi, which is coming from the normal density function, right? The density function. So we have an average of cave cluster, right? Of cave cluster, and sigma of cave cluster times pk, which is the weight, right? This is a reminder, this is a weight cave cluster weight, right? And here we need to sum up all the possibilities, right? So j equals 1k, capital K. So all the clusters. So we need to sum it up. xi, right? X j, and j right there, and the probability weight of the j cluster. Right. So basically, this is the simple ratio of being in a certain cluster, in the specific cave cluster, and this is divided by the sum of being in all the clusters, in whatever cluster we're looking at, by following the bias theorem. All right, so once we calculated that, now from this guy we can actually calculate the average because we have a probability of k given the data point, right? So once we have a data point, the average of a cluster, right? So we have various data points and we have the probabilities of being a cluster for these specific points. Right, so basically the average now is quite easy to calculate because we need just to multiply the actual value with the probability of being in a certain cluster, right? So basically we loop over all the observations, we take the probability of cave cluster given that observation, right? Given observation. So if the data point is not within, certainly not within that cluster, so this probability will be very, very low, close to zero. So that's why it will not be included into the actual calculation here, right? Multiplied by zero. But if the point is certainly in that cluster, so we will be, this value will be very, very high, close to 1, right? Close to 1. So that's why we will get complete xi, right? So basically we will get almost the exact value. So basically we are summing up all these values based, leveraged on the probabilities. And here we just need to divide by the sum of all the probabilities, right? So basically this is the normalization. This is like divided by n, right? Number of points when you calculate for the normal mean value. Okay, so this is basically the calculation for the mean and the calculation for the variance of cave cluster is very, very similar. We just follow exactly the same idea, right? We loop over all the values, right? Loop all the values, and we multiply the difference now, right? xi, which is basically multiply the difference error between the mean of cave cluster and the observation squared, right? So this is the normal way you would not use this probability, but since now we are looking into the certain distribution of the cluster, so that's why we need to multiply it by probability, right? And here again, we just divide by the same guy, right? This is n, This is pk divided by xi, right? So this is just like the normal number of guys, right, that are included into the cave cluster. Okay, and now we just, the final thing left, we just need to recalculate weights. So basically weights are recalculated quite simple. We just basically sum up all the probabilities for being in cave cluster, right, xi, and we just basically divide by the number of points, right? So basically normalized by the number of points. So this basically gives us a way that if we sum up all the p for all the clusters, we will get to 1. Okay, having with that said, so basically we have all the bits and pieces for the GMM algorithm. So now we can basically go and write it down. It will be rather quick. So let's do this like GMM EM algorithm, right? So basically as a 0th step, we will do init. So what we do for so init for d equals 1. Again, we are still in one-dimensional space, right? So our center vector will be reflected, right? All the means, right? Means. So basically means until the k. K, this is a number of clusters, right? So we have this guy initialized. The best initialization is actually the best like in k means plus plus, right? We want the maximum spread. So taking the random number, we want the maximum spread all the other numbers. So basically we can use the k-means plus plus initialization algorithm to find the right centers. Okay, so basically then the variances. So basically we initialize variances, right? So 1 until variance k, right? So basically to 1, so evenly distributed altogether, right? And all just one distributions, and basically the vector of the prior probabilities, we just basically 1 divided by k, right? 1 divided by k, and this is k number of these guys. So this gives us an equal priors, right? So equal priors. So basically we do not diversify weights in the beginning. So in the beginning we say that all the clusters are equal, and let's start the algorithm, right? So for the algorithm we have again the E step, expectation step, right? Where we for each I coming from 1 and n, so for each observation, each k coming from 1 until the k capital, for each cluster, we basically loop. This can be converted into the matrix, of course, and this is usually done by the matrix operations. But here we just do it like that. So for the first, we do the conditional probability of xi, right? Observing a certain point, giving the probability, right? Giving the distribution, k, and sigma squared k, right? So this is basically the same formula we had before, right? So n. We can put xi here and given xk and sigma squared k. I'm giving just this point because this point is needed in order to calculate the actual probability of being in this distribution, right? For the distribution point, given these two parameters of the distribution. Okay, and after doing so, we just basically inverse this by using bias theorem, right? We just basically calculate the probabilities of being in a certain cluster given these points. Okay, so this is an E step, expectation step. The other one is the maximization step. So basically we have probabilities assigned to each of a point. So now we, for each k from 1 until k capital, for each cluster, we basically calculate the average, right? So you know the formula, we just gave it. We calculate the sigma, right? Sigma of a k, right? And we calculate the prior probability for this guy. Okay, so step number 3, if M or S changed, just go to 1, right? Just repeat. Again, like in k-means, we basically loop it over and we do the updates, right? So we do the updates for the conditional probabilities, we inverse it, and then we shift the center and distribution, and we just repeat until the convergence, until the actual balance has been found. Okay, so basically what's happening here in the beginning for x1, right? In the beginning, we have certain probabilities here, right? Certain distribution is defined somewhere, like for instance, I don't know, let's put it somewhere. Okay, here we have, for instance, 2 clusters, right? 2 clusters, this is 1 and this is 2 defined, and we have multiple points spread around, right? Somehow spread around. So we basically calculate these probabilities here, the first conditional probability, right, for the point of being in a certain probability, and then we inverse. So we basically assign values, and we will see that the probabilities, the second inverse conditional probabilities will say that, for instance, this point is certainly, I will put into the downside, this certainly is 1. This certainly is even more certain that it is 1. This is certainly 1, right? And this is not so certain about 1. This will have 1 distributed between the 2 as well, right? So this is not so certain, right? This one is most certainly 2, right? 2 cluster, but has some touch, right, with the 1. This is basically, I'm showing up here, I just showed p x I given k, right? And here we just recalculate into a pk given xi, right? The probability of the cluster given this guy, right? So this is 2. This is more certain that 2, right? This is more certain and less certain that 1. This is obviously 2, right? This is obviously 2, and this is obviously 2. So once we did that, once we recalculate these probabilities, so obviously that this center will move to this direction, right? Because 2 is more represented over here, right? So this will move to that side, and this will move like the more spread, right? We'll have the more spread, right? And this one will stay somewhere here. But then after recalculation, we will see some changes, and obviously this will go along with the highest density of the points. Okay, so this is this basically was the these calculations is on the E step, right, and this move is actually on the M step, right? And then again we just basically loop over, right? Loop over until the actual convergence happens. Okay, so this was an example. I hope you understood that example. And so basically, application of this example into the multivariate case is more or less straightforward. But I need to show you that because it is quite related to the calculation of the number of the clusters. So multivariate case, right? Let's take a multivariate case now. So we have all the formulas, right? This is an algorithm. We have all the calculation formulas here, right? All the calculation formulas for both posterior distributions, for the prior, for the center, and for the variance. Okay, so basically we can give that as well for the multivariate case, so you will get some understanding about this. So basically, if you have, for instance, d equals 2, right? This is almost the only way that I can express it on the board, right? This is x1, this is x2. So now we will have, actually for each cluster, we will have a center expressed in 2 dimensions, obviously, right? So we will have xk first dimension and x average k on the second dimension, right? So this is a center, and this is a distribution, right? So basically distribution is expressed on both axes as well. So our center is actually now a vector, right? A vector of xk first and xk second, right? Center is the vector now, not a single value like before. And the variance is actually a covariance matrix here, right? We have a covariance matrix now. So basically sigma squared k1, right? And this is a variance. Sigma squared k2, which is variance on the other axis. And here we will have a covariance, right? Between 1 and 2. And here is sigma for k between 2 and 1. This is a symmetric matrix now, right? That expresses the distribution of the cluster in both directions, right? If we have more directions, so basically we will grow this matrix. We will grow this matrix along, so it's expressed on all the dimensions, all the combinations for the dimensions, right? So this is actually a covariance matrix now. Okay. So given that, obviously, we will have some change in the probability calculations, right? So basically, if you would like, I will give you again, I have here the formula, right? This is the vector now, right? In 2 dimensions, for instance. And we have the vector of mk and sk, right? These are 2 matrices now. And basically, the normal calculation now in this 2D space, now it's more complicated, obviously, because everything complicates, right? This is 2p times d by the power of d. This is sk. Okay, I just finished that. Okay. Okay. And this is the determinant. This is a determinant of sk, and if you want to calculate that, you can do with np Linaldo and determinant, right, given sk. So basically you can calculate that formula for the determinant. Then we have e and times minus half. This is xi minus mk. So this is basically difference, one vector difference to the other, transposed, multiplied by sk minus 1. This is actually sk inverse. Inverse matrix. So again, if you want to calculate NP Linaldo inverse sk, you can calculate that, and this is times xi minus mk again. Okay, so basically this is quite complicated formula. We will not go through that, but this is how you actually calculate the probability of observing is xi given this distribution. with v parameters. Okay, so any point in this 2D space is actually expressed how much it is probable that it belongs to this specific probability, right? Okay, distribution method, yeah. Okay, so basically now we have again, by following the Bayes diagram, we will have Bayes theorem, right? Bayes theorem, we will have again the probability. We change the probabilities from one conditional into the other, mk sk, right? And this is the weight. This is weight basically, okay? And here is just basically again, j equals 1 until the k. And this is again xi mj sj pj. This is just exactly the same, but now we have not a single values, but we have now the vectors everywhere, right? Okay. Now, basically calculations of xi average, right? Xi average is just the same. If you would this is k. Average of all the cluster is basically the same calculation, just like we had before, right? So basically we can loop over all the values, and this is probability of k, right? And xi, right? And xi again, and this is 1 and pk xi. This is just exactly the same, and the same would be for the s, right? So sk is just exactly more or less the same. So you calculate the difference and then square it up, right? Okay, I will not repeat because time's flying by and we're already one hour past. Okay, so basically after doing so, I'm just give you a small hints about how is actually EM is calculated. EM algorithm is constructed now. So basically it is constructed just the same way. So we have an initialization state where we have these, for the centers now, for the centers we will have a matrix now. So all the centers, since each center is a vector, so we have vectors here, mk, right, mk, and for each lower k is actually the average, mk1 and xk d. Okay, and these guys, this is actually can be used for the k-means algorithm utilization. So basically k-means plus can find the centers for the initial centers for the EM algorithm for the Gaussian mixture. Right, so initialization of S actually of the covariance matrices is a bunch of matrices right now, right? So this is a slightly more complicated, right? So these are the matrices, and SK is actually for the initialization is an identity matrix, right? So we have ones in the diagonal, right, and zeros here, right, and all the zeros. So this is identity matrix for the beginning, right? And for the weights, we basically again we have the same guy, right? The same guy for k. Okay, so this matrix, identity matrix, is actually d times d, right? So okay, so this is identity matrix d times d. Okay, so all the other steps like in 1D, right? So then first E step, second M step. So basically we calculate prior posteriors at first, then we calculate price in the centers, then we free and go to 1 or finish, Okay, so basically, if you have done that, if you have made these calculations and you have found the basically optimal points for the location of your number of K Gaussians, now you basically can use the likelihood function which we had for with the priorities in the logistic regression to actually calculate the performance, how well you did, right? How well you actually did while calculating that. So likelihood function for your given matrix X, right? So your aim, your goal is actually to maximize likelihood. Okay, okay, just throw it down. Let me put it lower here because I need to write down that you want to maximize likelihood. Likelihood, right? Maximize likelihood, right? Well, maximize likelihood. So likelihood is again can be written as a product of all the probabilities, right? Again, these are independent events, so we have a product of probabilities, and here the total probability for observing a certain event is actually a sum, right? By following the total probabilities sum, right? So for all the clusters, we basically sum xi this time, right? And this is for k and pk, right? And this actually is coming from this calculation is coming from the distribution, right? xi, and this is mk and sk, right? So this is already we have found the right centers, right? The center and the variance. So now we can calculate the probability of being in that cluster, right? Okay. So this all sum, right? This all sum towards the clusters. This is basically the probability. Sometimes it is written like the probability of xi in this model, right? For being in this model. Okay, so since again we have a product and this product is not so easy to calculate, so basically usually it is being put into the logs, right? So log likelihood, again, log likelihood for your data set, you can actually recalculate again. So this is again from the product we move into the sum, right? And this is log. It's much easier to work with and much easier to calculate derivatives. We will not be doing that, but just to show you around like that, you can basically, in most cases, use the log likelihood, right, as the final evaluation of your model. Okay, so obviously you will get the maximum log likelihood or likelihood, right, when k equals n, right, when k equals n, so you will get the maximum log likelihood because they will actually belong to the distribution they represent, they actually in. So there is a rule that you should be picking up the simplest model that fits, right? Simplest model that fits. There is a rule like this, right? So simplest we will put into commas, right? So pick simplest model that fits. And basically there are a couple of criteria used in order to find what simplest is. So one criteria we can write it down. So this is basically called bias information criterion. Bias information criterion, which can be written like maximize, right? We maximize value by p, right, by P, where the formula is log likelihood minus half of P log N. N is a number of points, right? N is number of observations. N is number of observations, and P is actually number of parameters or complexity, or the complexity of our model, right? The complexity of the model. So we want the model to be simpler, right? To be simpler so we can maximize this expression. The other one, along with that, is actually called Akaike information criteria. Information criteria. Right? It's very simple. It's just like that, but it's slightly different because now we want to minimize on P, where the formula is 2P minus log likelihood. Right? So basically, this way, in these criterions, we just basically include the number of parameters. So now let's take a look into some simple examples so you can figure out how to calculate the number of parameters. Right? So let's take our model is GMM. This is Gaussian mixture models, just like we reviewed. Right, and our example was D equals 1 in 1D space, right, and K was equal to 2, right, number of clusters was equal to 2. So obviously what we will have here, we will have a number of means was equal to 2 because we 2 clustered, right. Number of variances was equals to 2, right. And the priors, number of priors was equal to 1, because this is the other one is clear, right? This is degrees of freedom, right? So this is basically equal to minus 1. Because we're self-excluding, because we actually sum up to 1, so we exclude 1 because 1 is just known. 1 is not parameter, right? So we have just 1 as an uncertainty, right? So in this case, our P, we just basically sum it up, right? Sum it up, all these guys sum up. And we have P equals to 5, 2, 2, and 1, right? So this is the complexity of our model, right? So we basically take this P, plug into these formulas, we get the log likelihood, and we can calculate one or the other criteria. So basically, by changing slightly, for instance, let's have the again, we have GMM, right? We have dimension equals 3, and clusters equals 2. Let's say 2, right? So for the number of centers, right, we have D times K, right? D times K is equals 6. Right, 6 parameters for the centers now. Now for the distributions, right, for the variances, we will have D times D, right, and times K. Right, so basically D times D is 9, 9 times 2 is 18. As you can see, the number of parameters just explodes. Right, and the P is again equals K minus 1 is equals 1. Right, so now sum it up, and P equals to 18, 6, right, this is 24, and 1, 25. As you can see, increase in P, increase in number of parameters that we're using in our model, by just adding 1 dimension is tremendous, right? By 25. Okay, now please try to calculate if we would use the GMM, right? And D equals 3 and K equals 3. What is P, right? Try to calculate P. We just added one cluster into our model. Yes, so it's 38, right? As you can see, the tremendous increase. You just add one additional cluster, and you have a tremendous increase in the complexity of the model. So the rule of picking up the simplest possible model that fits is actually quite hard to meet, right? Because you need to really limit the number of parameters. And when you boost these parameters, you see that information criterions, either bias or Hierarchical, will go nuts. And this way, you basically, by following these criteria, you would have a metric that would not allow you to actually overfit to the training set, right? So basically, you can see that, for instance, if we draw a graph, draw the graph in, and for instance, we have the B here. We can have 5, we can have something like 25, like we had here, right? And 38, for instance, right? 38. This is not in the correct scale. It doesn't matter, but then we just basically, if we look into the bias information criterion, right, we can see that we have and basically like this, and then it goes flatter, right? So something like this. So you can see that it's going down. So basically the model becomes very complex, right? And this might not be a good thing to have. Okay, so you would be picking this one by following this criteria. Okay, and the other criteria, this is again for 5, 25, 38. This is P. This is the complexity of your model, and Hierarchical criteria, right? You can have something like this, and going up again, right? So that one, as a minimum, would be chosen as the best, right? This is the best model, and this is the best model for your choice. Okay, so there are some programs in industry. There are some programs that actually, when you use GMM, Gaussian model mixtures for the calculation, they include automatically these evaluation of these criterions, and you basically do not need to provide the number of K. You just provide a data set, and they calculate and they evaluate internally this parameter, right, this metric, one or other metric, and find out which is actually the optimal K for your data set, right, by following these criteria. Other than that, this actually does not include any knowledge of your data set regarding the subject. It just basically evaluates these metrics. And these metrics are not the golden rules, obviously, because you might look into the elbow method, into the other methods. So in order to evaluate how many actually parameters are needed for the choice of your data set. Okay, so this is soft clustering, and this was model based. So basically, we assume that our distributions of the observations within the clusters are actually distributed by normal model. And as I told you before, you can actually change this model into some other, and you basically need not to alter your model too much, right? This is just calculation of this posterior function, probability density function, right? And you can plug it in and it should work. Okay, but this is a more complicated case. I guess you understood it quite well, and you have some understanding about this kind of the clustering. Okay, I'm closing this. If you have any questions regarding that, please let me know. If not, then I will be moving into the other topic. Let me see. I just remembered where I wanted. Okay. I just remembered that today I have to give you the plan on your homework. Even though you have got a plan from Thomas, you got the tutorial, but I think that I might give you the some more elaborate explanation, the steps. But I don't see why I have, even though I wrote these steps. Okay, maybe I will remember them by the end. Okay, let's go forward. So in order to finish the clustering, I will give you two more methods. I will explain you two more algorithms of the clustering. So basically, we will go into a slightly different domain. We will go into the way of clustering without actually giving the number of clustering beforehand. So one of the clustering methods I'd like you to know, this is so-called hierarchical clustering analysis, right? Hierarchical analysis. This is basically a way of clustering that provides so-called dendrograms or trees, right? The hierarchical trees that can be used as meaningful taxonomies in order to explain relations between the observations. Okay, so basically there are two approaches, right? Two ways. One is so-called agglomerative, right? Agglomerative. When we start from bottom up, right? So with direction from down up, right? At first we treat each observation. Each observation is a cluster, and then we merge similar ones, right? And so on, and we continue until one, right? Until one cluster. Okay, this is agglomerative. So basically, so we combine small clusters into the bigger ones, right? And the other one is so-called divisive, where we start and proceed from up down, right? From up down, where at first we have all observations as one cluster, simply one cluster. All observations, one cluster, then divide until we go into each observation, until we basically reach agglomerative clustering startup position, until each observation is a cluster, right? Until we reach that. So basically, for the clustering, we need to measure the distance, right? So basically, distance between clusters. Distance between clusters is calculated by D for cluster key and L, right? And there are three approaches most commonly used for the distance between cluster calculations. Is so-called single linkage. This is the distance between the most similar observations. Distance between most similar observations in the separate clusters, right? So basically we have two clusters. Let's draw some here. We have two clusters, right? Two clusters, cluster and cluster. This has observations like this, right? And this one has observations like that. Let's put it like this. Okay, so two clusters. Single linkage is basically the the closest 2 points. So that point and that point are the closest ones in this drawing, right? So this would be the distance between the two clusters. This is the single linkage, right? The single linkage, how we calculate the distance between the two clusters. Then we have a complete linkage. This is the distance between most distant observations, right? So most distant observations, most probably that one and this one, right? So basically distance between clusters would be this one, right? This one, okay? So this is complete linkage. And obviously there is an average linkage. Average linkage, right? Linkage, average linkage, or it's called Ward's linkage, right? So this is basically the average between all the errors, average, right? So as the name states, average between all observations. Right, so average would be somewhere like, let me put it like here, and here, this would be the average, right? Average. Okay, so basically now we have a way to calculate the distances, right? So basically the agglomerative. In scikit-learn, you can find, and in tutorial Thomas has given you already, I think, the hierarchical clustering example, and this was agglomerative clustering algorithm, right? So it starts again 0, right? So initial point, each observation equals a cluster. So k equals n, right? So we have n clusters in the beginning, right? So step number 1, compute distances between all clusters. So basically this will give us a distance matrix, right? So distance matrix looks like more or less like this, right? So this is a square matrix where we have a k here, and we have k here, number of clusters, right? And we have in diagonal, we have zeros because this is the distance to itself, and this is a symmetric matrix, so we have distances here, right? Distance between 1 and 2 and so on, right? And how these distances are calculated, again, we had a special topic about how to calculate distances between points. So you can use any of these distances, right? Especially if we talk about the complete linkage or single linkage, it doesn't matter. So you can basically calculate any distance. For the average, in most cases, this is sum of squared errors is being used because you need an average, right? We need an average. And for the others, it just doesn't matter. You can use any distance, right? That was presented or not presented in this talk, in this lecture, right? Okay, so basically you have a matrix where distances between the clusters are expressed like that. So step number 2, merge two closest clusters, right? So k equals k minus 1, right? So we just merged, one disappears, and we have a common merged cluster between the two. Okay, and free stop if k equals 1. If we reached one cluster, if everything was merged into a single cluster, so basically stop, else go to 1, right? Go to 1, compute distances, merge, compute distances, merge, compute distances, and merge, and merge, and merge, and merge, and so on. So the good thing about this clustering is the following, that no need to provide a priori number of clusters, right? No need of k. So this is not a hyperparameter anymore. What is important here actually is the distance measurement. Is how to measure distances. There are various tricks, bits and pieces in how this distance can be achieved when you have a mixture of categorical and continuous values and so on. But I think for the practice work, if you would just do dummy values or ordinal values as 1, 2, 3, and you would do standard scaling, that would be enough. That should be enough, and this clustering method should work quite well. So basically a result that you can see, this is basically a dendrogram or the hierarchy, where here we have observations and here we have a distance, right? So basically individual observations, we can go down to the individual observations, right? So this should be an evenly decided. This is not a true scale, this is just a categorical scale of observations, right? And here the most similar ones, here the even more similar, right? With less distance. These two are merged, these two are merged, these two are, I'm just making up, right? I'm just making it up. So these two can be merged together, and these two clusters are merged together then, right? Let's merge these two, let's merge these two then, and let's merge these two somewhere up above, right? Okay, so as you can see here, I just made up a system, a model where we basically have two separate distant clusters that are important, that are distant quite far away one from the other, right? And they are quite homogeneous, right? Quite homogeneous between themselves, so they basically stand up as a separate two clusters. Okay, so this is basically quite good because you can interpret it well, and you can use it for the later showing it up for the audience, explaining it up, and so on. And you don't need to find the number of k. Later on, for actual usage, you can cut this this dendrogram at some level of distance, because sometimes number of observations is just too big in order to make this dendrogram meaningful. So basically, sometimes it's being just stopped at some point. Though algorithm actually works from bottom up, right from bottom up. But for display, sometimes it's just too many observations, so you need to stop. Okay, so this was the hierarchical clustering, which you can use from the scikit-learn, or you can try to implement this. This is not such a hard actually calculation, because once you can calculate this distance matrix, this is quite straightforward to find the minimal distance between two clusters and merge them into one. Okay, good. So the other clustering technique that I wanted to show, the last one actually, is the density-based clustering. Let me show it up. Density-based clustering. All right, so density-based clustering is another way of clustering data, basically finding the groups, right? So the most well-known and most frequently used is so-called density-based spatial clustering. So density-based spatial clustering of applications with noise, right? And this is called, the abbreviation is DBSCAN. DBSCAN. This is an algorithm which is quite often used, right, along with others when you want to cluster and you just don't know which one performs best, which one actually expresses best. So this one is an option to try it out. Okay, so it has a couple of important hyperparameters, right? One is the hyperparameters. One is so-called epsilon. This is the radius of proximity points. So basically, you have to define the radius where the points are considered to be close ones, right? To be close to the core point. Okay, and then you have so-called minimum points. So this is the number of observations within epsilon radius for so-called core point. Okay, so these two hyperparameters need to be defined. So once you define these two parameters, all the observations are being then classified, are being put into three classes, right? So observations are being put into one of the three classes, right? So basically, observations become core points. So core points, if for the point, if at least min points. So basically this, right? Min points fall within epsilon distance or radius at the point. So basically, if you have the so let's put it core point, right? The core point. This means it has at least 1, 2, 3 points that fall in the radius of epsilon, right? So this is basically an epsilon, and these points, this point is considered to be a core point, right? So basically, let's say this is the core point, right? So we can have another core point which would have 1, 2, 3, right? 1, 2, 3. Okay, 1, 2, 3. So our min points, let's say it is equals to 3, right? So if 3 points are within the epsilon, so we consider these points as to be core points. Okay, then the border points are the ones that have fewer than min points within epsilon, but lies within epsilon of the core point, right? So fewer points than min points, but within core point itself, right? So basically, these can be considered as being the border points, right? They don't have around themselves min points, but they are falling within these guys, right? So basically, let's put this as a border point. Okay, and then the last one are the other points or noise points. So basically, these are other which are not considered to be a core point or the border point, right? So if we have a point somewhere here, right? This is the noise point. Okay, let's change the look of this point. So basically put like that, like that. This one, no, it doesn't have any points. This one does not have any points. Okay, so these are the noise points. Noise points in this drawing. Okay, so basically having that, this is epsilon as well. Having that, we can define simply the algorithm of the DBSCAN, right? So basically, DBSCAN algorithm is basically two steps. One step is from each core point and connected core points. So these points that are connected together, that will go together, right, form a cluster, right? From each point, from each core points that are connected together, that are close together, just basically form a cluster, right? So number of clusters is basically defined by the core points, right? And then the second, assign border points to clusters. So basically, once we have formed clusters, right, by these core points, so after that we just basically assign all the border points to the clusters, right, and what's left is basically the noise, right? So basically, this algorithm is good because again, no need of k, right, but other hyperparameters, right? But you have other hyperparameters to consider. So basically, if you want to avoid of having k defined, but you need to define others, right? And what is good for it finds outliers or noise, right? In the sense of this algorithm. So basically, it basically finds the clusters and defines a noise, right? So basically, something like a classification algorithm, more or less. Okay, so classical example here is the following: that if we have a space of x1 and x2, and we have two half moons, right? So basically we have one half moon like this of points, right? And another half moon of points like this, right? So basically moving like that, inside. So for instance, or the situation where we have points like this and inside it, right? So points like this and inside a cluster. So in these situations where we have a complicated structure, k-means or EMM or hierarchical clustering, basically we would try to split these into the two like this. The other algorithms would split most probably into the cluster like this and the other cluster like this, right? So this would be more or less clustering for k-means, GMM, right? K-means plus or hierarchical. This is not actually correct because by eye we can see that these clusters are somehow interconnected, right? But for the DBSCAN with the right parameters, it would be actually possible to distinguish these two complicated structures, right? So this would be something like that. Because by density, it is capable of finding these structures, right? DBSCAN, and this would be a DBSCAN algorithm. Okay, so for structures like that, without K, you can use density-based clustering, and you can compare with other algorithms, etc. Okay, and there are even more algorithms, but these are the common ones, most popular ones, which is the first way to try. Okay, so I think that's it that I want to show now regarding the more or less what's expected for the clustering. Where I had it? Oh, okay. Let me see. Maybe I had it here written down because I don't want to mess. Oh, okay. I found it. Okay, I will open a new whiteboard, and basically this would be my poor man's plan for cluster analysis. Cluster analysis, right? So let's put this. This is the cluster analysis plan, right? You are not required to stick to this, but anyway, this is what normally I would require, right? So basically, at first, let's select and prepare our data set, right? So this is data set, meaning that we convert dummies, right? Convert categorical values to dummies, or ordered values, and so on, right? So you have to identify which values are for what, and you need to convert it to this. Because I assume that you would be clustering continuous and categorical values in one set. Okay, then I would require to scale it, scale to STD, to standard scaling, right? So basically applying normalization is required here, because otherwise you could get some inconsistent results, because here is where the magnitude, the absolute values are very, very important, right? Okay, then train, valid, and test, split. Again, we just split. You can split into the training test, but valid is good if you're considering to actually to choose the best K, right? If you would be choosing, if you would be optimizing on the clustering parameters, right? So now at least 4K equals 1 until, let's say, 10 or more, right? Whatever number you choose, right? It's up to you. You just basically loop your algorithms, loop your UII algorithm, right? You can loop k-means plus plus, so you can use the GMM, right, which we talked about. You can use hierarchical. Hierarchical is not to be used here because it is not dependent on K, right? It's not dependent of K. Okay, you just basically looped it up. You can use then elbow method, right, to choose, or elbow method, right, to choose. You can use elbow, you can use machine learning elbow, or you can use the R² adjusted, right, to choose the right K. Then obviously you can use the silhouette coefficient and plot, right, and plot to interpret. Then you can do the interpretation. Alongside, once you did that, once you have found at your understanding the best, the optimal number of clusters, right, you can do the comparison, the hierarchical clustering, because it gives the hierarchy for you, right? If you would use the same distance measure as you did for these clustering techniques, you can basically try out and do hierarchical with the same distance or the other distance. It's up to you to choose, right? But it gives you a good mean to interpret. This gives you a way to look into the dendrograms, right? Okay, you can use even hierarchical clustering or DBSCAN, and just to try it out. This is all available in scikit-learn, right, library. Or you can implement this, and you actually can replace from this within K lookup method. Okay, and after doing so, once you do the interpretation, once you combine all results, you can basically write 3 conclusions as per requirements for the task. Okay, so this is not a complete, this is not required, but this is what normally I think you should be following more or less. But this actually depends on the algorithm you're choosing. For instance, if you would implement the hierarchical clustering, if you would construct the dendrogram, then you should not be relying on the K, right? But then once you did the hierarchical clustering, and once you have found that, for instance, it is meaningful to rely on, say, 5 clusters, try to find out these 5 clusters with the other algorithm, other method like k-means plus, for instance. Try to find it out and try to compare. What are these composed of? Because basically the silhouette coefficient and the composition, some cross tables, cross checks that are very good when you would like to see the complexity, what actually is composed of each cluster, so you can find out some insights for your conclusions. Okay, so that's it for today. Let me know if you have any questions. And next week there's a deadline. There's going to be no seminar, so basically just your homework and submission to the usual place. If you have any questions regarding today's lecture or the assignment, let me know. By the way, all the videos for your convenience, all the lectures will be already put into the YouTube. So I will put this lecture as well, so it will be much easier for you to find out and to follow it. Okay, if you don't have any questions, then thanks for your attention and have fun with clustering. Can you upload to Moodle the whiteboard? Yes, I can. Yes, I can, sure. And what I will do, I will put link to this to these videos in YouTube, because I find it quite clumsy to look up these videos in this system.